Right, we've had a request from Sherry George to cover the Physics Paper 6 Alternative to Practical. That's from October-November 2016. The code is 0625/63. There we are, and this of course is the Cambridge International Examinations. So let's have a look at that now.
Let it begin! Let it begin! Let it begin! Wait!
Question 1. Some students are investigating how the surface area of water exposed to the air affects the rate at which the water cools. They are using the apparatus shown in figure 1.1. Beaker B is bigger than beaker A. So let's look at that. There we are, so we can see that nice and clearly, just how it's set up. 2 beakers, 2 thermometers in it. A. The students pour 75 centimeters cubed of hot water into beaker A and 75 centimeters cubed of hot water into beaker B. They immediately start a stop clock. Record in the first row of table 1.1, the initial temperatures theta of the water in beaker A and in beaker B as shown in figure 1.1. Alright, so we're going to have to read the thermometers in the beakers. There we go, and if we look nice and close we can see that looks to be about 82 degrees Celsius. This one over here seems pretty much dead on 80 degrees Celsius. There we are. So let's put that information into the table. You don't have to put the 0.0 here. The only reason I have is because some of them have a half a degree put in there as well to show what they're trying to read to. But you'd be fine putting in 82 and 80 without putting the decimal point. That's absolutely fine. 2. The students record the temperatures theta of the water every 30 seconds. The readings are shown in table 1.1. Complete the headings and the time t column in 1.1. Alright, so we have to complete the headings and the times. So let's begin. This of course is time. It's measured in seconds. It tells us it's every 30 seconds. Theta is in degrees Celsius here and degrees Celsius here. There we are. Alright, so the first one 0, then it's every 30 seconds, so 30, 60, 90, 120, 150 and 180. There we go, beautiful. Describe 2 precautions which should be taken when using this apparatus to ensure the temperature readings are as reliable as possible in the experiment. Right. Step number 1, whenever you're reading any type of equipment that's got a scale on it that isn't located directly on the thing that's moving, you have to watch out for parallax error. So, the first thing, and it comes up an awful lot in this type of question, is to read the scale at 90 degrees. So read the scale at a 90 degree angle. Or you could say perpendicular. 2. Well, what's going to happen when you pour that hot water in? You pour that hot water in, the readings change. So what you should really do before you start the experiment is wait until the reading stops rising. That's a very important thing, very important point. There we go. Part C1. Write a conclusion stating how increasing the surface area of the hot water affects the rate of cooling of the water. Justify your answer by reference to the results. Okay, so let's look at what's happening. We've got a time passing, and this time is 180 seconds. During that 180 seconds, beaker A loses 9.5 degrees Celsius. And beaker B loses 15 degrees Celsius. So much the temperature has decreased by. So it seems to me that beaker B is losing thermal energy more rapidly. So let's put that into an answer. So over 180 seconds, temperature drop in A is 9.5 degrees Celsius and the temperature drop in B is 15 degrees Celsius. So that tells us that the temperature of B drops more than A in the same time period. Right, let's look at the next part. So C2 suggests a change to the apparatus to make the comparison of the effect of surface area on cooling a fairer test. Explain why the change is an improvement and state the likely effect on the recorded temperatures. Okay, so let's look at this. Here it's talking about the surface area on cooling, the effect that has, which means we want to minimise any other effects. Let's go and look at that picture. There we go. So the surface area is just this bit up here. And at the same time, the way it's set up, we're going to lose a lot of energy from the sides, from the base, and that's the same on both of them. What we want to do is minimise that. So probably the best improvement we can make to it quickly would be to insulate the sides and the base. And if we do that, then we're making sure that heat can only be lost from the surface. And that is exactly what we want. Suddenly we're only dealing with the surface of the liquid there. And that means that over the time period, a same time period, we'd lose less energy. It would only be from the surface. That means the temperatures would be higher. So there we go. The change, insulate the sides and the base of the beakers. The explanation? Well, if we do this, the heat loss is only from the surface. And the effect on temperatures, as we said, the temperatures would just be higher. Okay. Part D. Students in another classroom are carrying out the same experiment. Suggest a factor that they should keep the same if they are all to obtain similar temperature readings. Well, I think at that point we start off with hot water. It should probably be best if it's all the same temperature, so the initial temperature of the water should be the same. There we go. Let's look at question 2. Question 2. Some students are determining the focal length of a converging lens by two different methods. They are using the apparatus shown in figure 2.1. We've got an illuminated triangle with a lamp behind it and a lens going onto a screen. Okay. A student sets the distance u between the illuminated triangle and the lens to 20 centimeters. She moves the screen until a sharp image of the triangle is seen on the screen. Measure h0, the height of the illuminated triangle, as shown in figure 2.2. And then measure hi, the height of the image shown on the screen, as shown in figure 2.3. So let's go and look at them. There we are. Now, what it looks like it's asking us to do is measure the inside of the triangle. Okay, so there we go. And measuring this here, what I get is 1.5 centimeters for that height, and for hi, the height of the image, I'm getting a measurement of 4.0 centimeters. Now don't worry if your measurement's slightly different, because if you've printed out on paper it may well have resized the PDF or the image, wherever you got it from, to fit the paper. So you could end up with it being a few millimeters one way or the other. The key point though is it's asking you to measure the inside of the line, the white bit of the triangle if you will, not to the end here, but to the inside bit here. Alright, so let's put those measurements down. And make sure that little decimal point there is nice and visible, and make sure that you've got your units in as well. Very important to remember those. 2. Calculate a value m for the magnification using the equation m equals hi divided by h0, the image height divided by the original object height. Okay, well, nice and straightforward. 1.5 divided by 4.0. Of course, they're both centimetres, but they'll cancel. So what you're left with is just a ratio. It's just a number as well. And the actual value that we get, if we follow that through, is 2.6666, and it goes on. Now, obviously what we've got here is two lots of two significant figures. So your best bet for m, two significant figures, 2.7, and no units on that. Now, for part 3, we've got a calculation which is involving the value for m we just calculated. Okay, so f1 equals, let's read through the question. Calculate a value for the focal length f1 of the lens using that equation. F1 equals u times m divided by m plus 1, where u is 20 centimeters. Alright, so what we get is 20.0 centimeters times m, 2.7 divided by 2.7 plus 1, which is 3.7. And if we follow that through, we will get a value 14.6 centimeters. Now, if you were to do this, but use, say, the actual calculated value, not the rounded value, there we go. If you were to actually use that value, 20.0 multiplied by 2.6666 and so on, divided by 2.66666 and so on, plus 1, so 3.666, then what you would get, there we are, that would give you a value of 14.5 centimeters. Of course, because centimeters on the top there. Either of those answers is correct, and if you check the marking at the back, you'll see you get a mark for 14.6 and you get a mark for 14.5. So whichever one you put down will be absolutely fine. Alright, so we go, let's put, say, 14.5 then, why not? And the units, make sure you've got the units in there as well. Okay, let's look at the next part. Part 4. Describe one difficulty which might be experienced when measuring the height of the image. Suggest an improvement to the apparatus to overcome this. Alright, let's look at the apparatus. What's happening is we have to measure the image on the screen. Okay, so how are you going to do that? Well, first of all, you're going to put your ruler here, and then you're going to hold it with your hand. Then you're going to try and look at it from over here. And hopefully none of these things create a problem, because what you've got is your image being formed all over your hand and over the ruler. So it creates a bit of a mess. One thing you can do is maybe use a grid on the actual screen. That's quite a nice way to solve a problem. So a difficulty would be trying to measure the image would put the ruler and the hand in between the image and the screen. And the way we could solve that problem, the way we could improve the experiment, would be to place a grid on the screen and use the grid to measure. B. The student adjusts the position of the lens so that u equals 40 centimeters. She moves the screen until a sharp image of the triangle is again seen on the screen. Figure 2.4 is a scale diagram showing her result. Right. On figure 2.4, measure the distance between the lens and the screen. Now I did this and I got a nice round measurement of 5.0 centimeters. Again, don't worry if you're 1 millimeter or so off. It may well be the case that your screen's been resized, but measure it carefully, and the key point is you want to measure it to the centre line of the lens. I've drawn a little dotted line here. So that's what you're looking at, centre point of the lens when you measure it. That's between the lens and the screen. So you'd want it to the front part of the screen, just there. Okay. Now figure 2.4 is drawn to 1/5 scale. Determine the actual distance v between the lens and the screen in the experiment. Well, they'll be 5 times bigger. So 5.0 centimeters times 5 will give me 25 centimeters. And remember, the units are very important. Make sure you're writing them down. Part 2. Calculate a second value, f2, for the focal length of the lens using the equation f2 equals uv divided by u plus v, where u is 40.0 centimeters. Well, we already calculated v in the last section, and that was 25 centimeters. So let's write that down. There we are. And if we carry out that calculation, f2 is given by 40 times 25 divided by 40 plus 25. Now, that then gives us 1000 divided by 65, which is 15.4. Now, let's have a look at the units. What units this should have, the 15.4. What are they? Well, let's look at where the calculation takes us. We have 40.0 centimetres multiplied by 25 centimetres divided by 40 centimetres plus 25 centimetres. That gives us 1000 centimetres squared divided by centimetres. Of course, that's going to cancel. We're left with centimetres as a unit. So F2 is 15.4 centimetres. Why is it 15.4? Well, because this is actually 40.0 and this we can put in 25.0, we could leave it as 25, doesn't matter. We get 3 significant figures and 2 significant figures. We can go with the 3 significant figures there. If it was just 2 significant figures and 2 significant figures, we should keep it as 2 significant figures. But because one's 2 and one's 3, really it's a little bit more our choice. It's probably better to go with the 3 significant figures in the answer. The student suggests that F1 and F2 should be equal. State whether the results support this suggestion. Justify your statement with reference to the results. Well, if we remember F1, well, that was 14.5 centimetres. And what we can see is a pretty close in value. They're not far enough apart for us to say they're not related. So they're close enough, we'd probably say they're related or they're equal within the limits of experimental accuracy. Why? Well, because it's not a very accurate experiment. It's only about 6% really separating those values. So there we go. The results are equal within the limits of experimental accuracy. Part C. State one precaution not included in your previous answer that you would take to make the experiment reliable. Okay, one thing that's quite useful you can do is put a mark on the lens holder to show the centre of the lens, because it's difficult to measure from the centre of the lens. That would work. Another thing you can do, use a dark room. If you're trying to see these little images as they're being formed, a dark room is a good way to do it. There's 2, but we'll just need 1, so place a mark on the lens holder to show the centre of the lens. There we go. Question 3. A student is investigating the resistance of a lamp. He is using the circuit shown in figure 3.1. The student connects a crocodile clip on the slide wire to give particular values of the potential difference V across the lamp. He measures the current I in the lamp for each position. Figures 3.2 to 3.6 show the ammeter readings for these values of voltage. Read and record in table 3.1 the values of I, the value of the current, for each value of potential difference V. Record each value to 2 significant figures. Alright, well, let's look at them. What we can see is there's 5 gaps between each point. So between point 1 and point 2 there's 5 gaps. So each one represents 0.02. So this here is 0.12 amps. This reading here is 0.15 amps. It's right in between point 1 and point 2. This one here, 0.17. Here we go, this one, 0.19 amps. And finally, 0.21 amps. There we go, let's fill out our table. Alright, so now B, calculate and record in table 3.1 the resistance R of the lamp at each value V. Use the equation R equals V over I. Here we go, this equation there. So putting that into our calculator, there we go. It gives us 4.2, 6.7, 8.8, 10.5 and 11.9. There we are. So the table's now completed. One thing you will note is what I'm doing as I run down the table is not concentrating in the number of significant figures as much as concentrating on the same number of decimal places as we're going down the table. That's just good practice, really. Right, plot a graph of the resistance against the voltage. Now, if you look at the resistance, it goes from 4.2 to 11.9. So it goes really from 4 to 12. I've got here 1, 2, 3, 4, 5 squares I can use. And I've got to get from 0 to 12. See, in an ideal world I'd have 6 squares for that. What I can do though is if I go from 4 to 12, then I can use, let's see, 4 squares. Each square will give me 2, so it goes 4, 6, 8, 10, and 12. And then, because this bottom bit has to jump to get there, we put a little jump in the axes. There we go. Problem solved. And this is R in ohms. Always label the axes. There we go. And V in volts on this axis. So it's always important to make sure you're following the instructions but label the axes. And down here we're only going to go from 0.5 volts to 2.5. 1, 2, 3, 4, 5. That's perfect. So we'll do 0.5, 1.0, 1.5, 2.0, and 2.5. There we go. And now the points that we have take up most of the screen, certainly most of the graph, which is what we need. Something we should always ensure that we're trying to do. So go across it and highlight the axes. Make sure it's nice and clear what's going where. Okay, so now we can plot the points that we have and see what that gives us. Here, 1.5 is 8.8. 2.0 is 10.5. Finally, 2.5 is 11.9. Alright, and what we can see there is if we try and do a best line fit, it's going to be a bit of a curve. So we'll try and draw that in nice and carefully. Always tricky to do. There we go. Should be a smoother line than that. The reason it isn't is the surface I'm doing this on isn't ideal. But there we go. So, you know what? I'm going to label that. Do better. Do better than me. Now, it's always tricky to do these curving lines, but the best way to do it, the way I find works, is to use the heel of my hand and then just allow my hand to move round in a circle and move my fingers in or out, depending whether the circle is getting wider or narrower or the line's getting further away. And that's the best way, or the easiest way to do a curved line best fit. Okay, so let's see what's next. D. State what the shape of the graph tells you about the change, if any, in the resistance of the lamp during the experiment. Well, what do we see? As the voltage increases, the resistance increases. But we also see that the resistance starts to increase less for the same increase in voltage. That's why it's a curve. So let's write those down. So as the voltage increases, the resistance increases. And the resistance increases less for the same increase in voltage as the voltage gets bigger. There we go. Let's look at part E. In this type of experiment, it is possible to change the current and potential difference for the lamp by using a variable resistor rather than a slide wire. On figure 3.7, complete the circuit diagram to show a variable resistor used for this purpose. Okay, so just completing the diagram. Here we go. Resistor, variable resistor. And then always make sure all the lines are completely joined. There's no gaps specifically around about here, or here, or here, or any of these points, because they'll check them. When they're going through and marking it, they will look to make sure there's no gaps bigger than 1 millimeter. If there is, you might lose marks. Question 4. A student has noticed that different types of paper have different strengths. Plan an experiment which will enable you to compare the strengths of the different samples of thin paper, prepared as shown in figure 4.1. We've got a wooden block, we've got adhesive tape, we've got hooks on either side. Write a plan for the experiment, including the additional apparatus needed, instructions for carrying out the experiment, including any precautions you will take, and what you will measure. Oh, a few more things. How you will present your results, how you will determine which paper is the strongest, and the variables you will keep the same to ensure the comparison is a fair test. You may draw a diagram if it helps to explain your plan. Alright, well straight away we're going to want to draw a diagram, certainly. It always makes it easier to explain if there's a diagram showing what we're trying to say. But let's just briefly talk about what's a good way to do this type of experiment. Here we go. We want to measure the strength by hanging things off of it. So what might not be a bad plan, here we go. Basic sort of setup here. We've got our little clamp stand, then here we've got maybe a spring balance or a Newton balance holding the paper. Something like this. And then on the end here we'd probably have a mass hanger, and we would add weights to it. And this would probably mean that we'd have to do it at the edge of a table because we'd run out of space. There we are, so this would be the bench. There we go. And what we'd be doing is just adding weights to it until the paper breaks and this falls down. So we're going to want to put something under here, soft mat or something, to catch the weights as they fall. Something along those lines would be a good way to do it. Now when you get to these questions, it's a good idea, just do a little sketch for yourself before you start answering the question. Just try and make sure that your idea is going to work and that it's reasonably solid, reasonably sound. Okay, now just by doing a little sketch here, it will help you think about the information you want and the stuff that you want to pay close attention to. For example, here it's asking us to compare the strengths of different samples of thin paper. So it seems as though what they're asking us to do is find out the strengths of the different types of paper. But that doesn't mean that we then have to do ranges of the widths of the paper. We might just have to do several measurements for the same width of paper. We'd probably expect them all to have the same thickness and the same length. But one set where we're measuring the breaking weight several times would probably give us a really nice set of results. So maybe we might end up with a situation where it's all 3 centimeters wide, for example. Yeah, so 3 centimeters, maybe 2 centimeters, doesn't matter. We just have it so it's the same thickness. That's our key point. And then we change out the samples. We might measure sample 1 3 times, sample 2 3 times, sample 3 3 times. And then that would enable us to come up with a set of results. We then average the results. And then when we pull out the information, we probably have the breaking weight, up here, which would be in newtons, and then along this way we would have the sample, and we'd do it as a bar chart. And we'd say, hey, you know what, this one took the most weight to break. So we'd be able to do a direct comparison in that manner. And of course we just have the sample 1, sample 2 and sample 3. That would probably be a reasonable way to take to approach this experiment. So, pretty long, bit complex, but certainly doable. Now what we have to do is take this information that we've just come up with, this idea, a series of ideas, and write them out. So, let's give that a go. Alright, so now we've got a better idea about what we want to do, what we can do. Start doing a better diagram. Just to be clear though, it doesn't have to be much better. There we go, it's really just a bit of a sketch. Something to remember when you draw these little items. You don't have to draw three-dimensional things. They don't have to look like the world's best art exhibit. You're just drawing something that you can label, it's convenient, and it communicates what you're trying to do. Alright, so first of all, the first part of the experiment, we're going to set up the equipment as above. That's here. There we go. Then, so just a quick list of what people will need. Need a clamp stand and boss, spring balance, paper samples, a soft mat to catch the falling mass. And I've left a bit of a gap there for anything else that comes up as we're writing through this. Take 3 strips of each type of paper. All sample strips should have the same length, width and thickness. So they're my control variables. Right, so what we want to do then, attach each sample to the hook at the base of the spring balance using the ring. Suspend a mass hanger at the base ring of the paper. Slowly and gently add masses to the hanger, ensuring the paper is not damaged until the paper sample breaks. Record the reading on the spring balance when it breaks. Once it breaks, repeat with the 2 remaining samples for that paper type. Repeat this for the other paper types and record the results below. Plot the average results in a bar graph with average force on the y-axis against paper type on the x-axis. The tallest bar graph is the strongest paper type. So just this is the table for recording results. Paper type, breaking force 1, BF1, BF2 and BF3, and of course the average one at the end there. There we go. So that should do it nicely. That about answers the question, I think, pretty well. Okay. So, hopefully you found that useful. It's been quite helpful for you. If so, please feel free to like and subscribe. If you've got anything that you want me to go over, then just leave a note in the comment section below. Have a great day.